Okay, so what we're going to do today is we're basically going to review everything we talked about for that nuclear physics chapter, finish that up, and start on our new chapter, which is going to be our first real chemistry chapter. Okay? So if you remember back, all right, way back the week before spring break, we started talking about atoms. What do all atoms have in common? What are three things found? They're all matter, yeah. That's what I was looking for. Protons, neutrons, and electrons. Okay. So in the center of every atom are the protons and neutrons. Orbiting around the protons and neutrons are the electrons. And what do we call this region in the center where the protons and neutrons are? Nucleus. Okay. Remember, this is what makes atoms distinct from each other. Right? The number of protons, neutrons, and electrons. And we used a couple things, a couple numbers to describe this. All right? So let's start talking about carbon, for example. Carbon 13.6. What do I call this top number? Yeah. The bottom number is the atomic number, and the top number is the mass number. Okay? And remember, the atomic number tells us how many protons we have in a given atom, while the mass number tells us protons plus neutrons. Okay. So carbon 13.6 has 6 protons. What else is 6? Nothing. The electrons, right? Because we talk about atoms to start with in their neutral state. So that means if I have 6 positive protons, I have to have 6 negative electrons to balance that out. To find the neutrons, I have to take my mass number minus my atomic number, so 7. And remember, it's this number of protons that makes carbon carbon. So carbon has 6 protons, atomic number of 6, all right? If an atom doesn't have 6 protons, it's not carbon. Okay? If it has 7, it's nitrogen. If it has 5, it's boron. But the number of neutrons can change. What do I call that then if I have carbon that has 8 neutrons? Isotopes. Okay? Isotopes are still the same atom, just with a different number of neutrons. Good. Now, we spent a decent amount of time talking about radioactivity. What does it mean when an atom is radioactive? Yeah, it's how unstable it is. Because if we talk about these smaller atoms, right, if we have this balance of protons and electrons, everything's happy, everything's fine, okay? But when we start getting to these bigger atoms with a bunch of protons in the nucleus, depending on the number of protons and neutrons, they can get unstable, and pieces can break off, okay? So for example, uranium is radioactive. Okay? Uranium could have some piece break off and become thorium. How would I figure out what that piece was that broke off?
The atomic number?
Yeah.
2 as an atomic number?
Yeah. Because we have to have the same atomic number that we started with and that we ended with. So if I start with 92 here, I have to end with a total of 92. It doesn't matter that it's in 2 separate places, but I have to end with 92. So here I have 92 on the left, 2 plus 90, 92 on the right. Same thing with the mass number. Mass number, I start with 238, end with 234, so I'm missing 4. What has an atomic number of 2? Yeah, helium. And so which type of decay is it that looks like the nucleus of a helium atom? Yeah, alpha. Okay.
How are you supposed to figure that?
Well, because there's only 3 types of decay that are going to happen. Alpha, beta, and gamma. Okay. That's kind of the nice thing about natural radioactive decay. Okay? Uranium left to itself is going to decay over time, but only one of three things is going to happen. So if it's a helium nucleus, it's alpha. Okay? What about if I have carbon-14 and it turns into nitrogen 14-7? What numbers am I missing here?
-1.
-1 and 0. So what type of decay has a mass number of 0 and a -1 for an atomic number? Beta. Okay? And so remember, beta particles are just electrons. And I know they are kind of weird, okay? Because a beta particle, all right, it doesn't have any protons or neutrons, so its mass number is 0. But it has a -1 for its atomic number because we can kind of think of it as being the opposite of a positive proton. Okay? So a beta particle, 0, -1. And then finally, let's say we have plutonium, 24494, and it emits a gamma ray. What's the mass number of a gamma ray?
0, 0.
Yeah, it's just light. So really what's happening here is this atom is just releasing a little bit of energy. So if it releases a little bit of energy, it's still going to be plutonium. Okay? And so these are the only three things that can happen. But no matter what's happening, what we have to keep in mind is that the numbers on the left are going to equal the numbers on the right. The mass number is not going to change. The atomic number is not going to change. Yep?
I have a question about the isotopes. If we're supposed to say what it is, like, are you going to give us, like, carbon-6 and carbon-8 and then ask what they are? Or, like, or is this just know that carbon-6 is 6?
No. You don't have to memorize that. So all of these are isotopes of each other. So we don't say, we say, give me a second. Okay, so carbon 12-6 is the most common isotope of carbon, but it's still an isotope of carbon. All right, carbon 13-6, okay, carbon 14-6, these are all isotopes of carbon. Yeah, they're less common. So it's not that you have one real carbon and the rest are isotopes, they're all isotopes. Does that make sense?
Is that just with carbon? But
No, that's with everything. Okay. So for example, I mean even like chlorine. Okay. The most common isotope is chlorine 35, but there's also chlorine 37. You don't have to memorize that. Okay. I'll tell you that. What you need to know is that if I ask you on a quiz or test, okay, I have carbon 13-6, and I add 2 neutrons. Is it still carbon? Yeah. Okay. It's just a different isotope. All right. But at the same time, if I have carbon 13-6 and I take away 2 protons, is it still carbon? No. If I take away 2 protons, now it's beryllium. Okay.
I have a question.
Yep.
Okay, whenever you take away the protons, that changes the element.
Yes.
And, I mean, an element can just change.
No. What we're going to see as we go on, these reactions are very difficult, all right, to happen. They can change, but they're not that likely. I mean, if I want to do a chemical reaction, I can just go down to this chemistry lab right here and do a chemical reaction. Or I could just bring some vinegar and baking soda in here and do a chemical reaction. But to do an atomic reaction, I need something like a nuclear reactor, nuclear bomb, or a star. So they're not that common, okay? Now, this decay process does happen naturally.
That's what I was talking about, the decay.
It just happens, yes. But for the most part, these are very, very long processes. So when we talk about half-life, we're talking about how long something happens. So if I have carbon 14-6, okay, like we just did, carbon 14-6 will emit a beta particle and become nitrogen 14-7, okay? But the half-life of this reaction is about 5,000 years. Okay? So it's very, very slow.
So it takes that long for it to turn into the separate element.
So if I start with 200 grams, it takes 5,000 years for it to go to 100 grams. Okay? So after 5,000 years, 100 grams of this carbon-14 would undergo this decay and become nitrogen.
Okay,
Yeah. Okay? And remember, if we're talking about half-life, remember, this is all probability, so it's just going to keep decreasing by half every 5,000 years. And that's why especially, all right, most half-lives are very long. And the things that have short half-lives don't stick around for long, all right? They're gone really quickly. That's why we have all these like artificial atoms and elements down here, all right? All these things are around for a couple seconds, then they're gone, all right? What we have around us right now are things that are stable, okay? The iron in this desk leg is stable. It's not radioactive. It's not going to decay over time, okay? But some of the uranium in the crust, uranium-238, has a half-life of a few thousand years. So slowly it's going to break down. Does that make sense? Now what we ended with last week was we started talking about nuclear fission. All right, because all these radioactive things we talk about are all natural. They're all eventually going to happen on their own. But what we can do is with a few of these atoms, we can speed this up. So if I take uranium-235 here, let's do a separate one. If I take uranium-235 and I shoot a neutron at it, instead of waiting for that uranium atom to slowly either emit an alpha, a beta, or a gamma particle, I'm going to make it split right away. Okay? And so in this case, this uranium is going to split. And we'll say one thing that could happen is it could split into iodine, let's say 153, along with something else, and let's say 4 neutrons. How am I going to figure out what that something else is?
When you first multiply the neutrons, that change the mass number and the atomic number?
Yeah.
The atomic number
Because,
will stay the same.
yeah, because if I have 4 neutrons, all right, each of those with a mass of 1, that means the total mass of all those neutrons is going to be 4. Okay? But then just like we did before, I have to have the same mass number on the left, the same mass number on the right. So if I start with 236, 235 plus 1, that means I have to end with 236. Well, right now, I only have 104, so I'm about 132 off. Okay? So that means whatever I'm missing is going to have a mass number of 132. Same way with the atomic number. I start with 92. Okay? These neutrons don't have any atomic number. Okay, but this iodine has an atomic number of 53. So 92 minus 53, I'm going to get 39. So now I can go look at the periodic table and say, what has an atomic number of 39? Why? Okay, and remember, you'll have your books that have the full names of everything in them, all right, for the test, all right, the periodic table in your books. Okay, so we're actually going to make Y, which is yttrium. Okay, so this is basically an artificial version of what we've already seen. What we're doing is we're not waiting for this uranium atom to slowly decay over time. We're going to shoot a neutron at it and make it happen right now, really quick. Why don't you guys try one of these? Right. Okay. Let's say this time I'm firing this neutron at plutonium. Find plutonium. Okay? And this time it's going to split up into krypton 102, 36, something else, and 3 neutrons. See if you can tell me what that other piece is going to be using what we've already used. No, I'll have it back for you on Wednesday. Sorry. I don't have your quizzes graded, so I'll have them back to you on Wednesday. Okay. What's your mass number on the left?
140. On the left.
Yeah. 245. Okay. And so on the right to start with, we have 102 plus 3, so 105. So you're right, we're missing 140. Okay. Well, what's your atomic number? You start with 94, end with 36. So what's your new atomic number? 58. So once again, we can look at the periodic table and find 58 somewhere. Ce, cesium. Well, maybe. We'll say it's cesium. Okay. So that's it. All right. So really, all of these reactions just boiling down to getting the mass number and atomic number to be the same on the left and right. And once you have that atomic number, just remember it's the atomic number that tells you what atom you have. Then you can look at the periodic table and say, okay, what is it? Which one do I have? All right? Now, this reaction is the same reaction that's happening in nuclear reactors and nuclear bombs. Okay? The only difference between the two is that in a bomb, this happens in the span of half a millisecond, whereas in a reactor, this happens over the course of a year, 2 years, 3 years. Okay? But that's the only difference. And so really what I want us to understand today before we go any further is how a nuclear reactor works. Now we can do that because really this is pretty simple. Okay? Thanks. Anyone know how a steam locomotive from the 1800s works? Steam locomotive from the 1800s. Yeah.
They heated up the water in that the big part in the front.
Yeah, they heat up water. Ran on coal, right? So use coal to heat water. The steam turns the wheels, all right? Or turns a turbine or whatever. Okay? Really, that's the exact same thing that's going on in a nuclear reactor. Okay? Except instead of coal, we're using uranium. Okay? So every nuclear reactor starts with the fuel rods, which are basically that uranium reaction we just saw before. Okay? But now remember, I said the one difference between a reactor and a bomb was control. Okay? How are we going to control this reaction? Because remember, if one neutron breaks one uranium atom, and each time I do that, I get 4 more neutrons, which go to make 4 more uranium atoms. Then I have 16, then I have this exponential increase. What should I do to slow down this reaction? Think about that for a second. What can I take out of this reaction to slow it down? The neutrons. Okay? If I can do something to maybe say, well, instead of 4, let's take one of those out. So it's only 3, or maybe only 2, or maybe only 1.5, okay, on average. And that's exactly what these control rods do, okay? If I lower these control rods in here, they absorb those neutrons without starting new nuclear reactions. But if I raise them up, all right, I speed up the reaction because I'm letting all those neutrons hit more uranium atoms. So by moving these control rods up and down, I can control the speed of this reaction. Now, why do you think it's critically important that these are held in place by an electromagnet? We have a lot of thinking today. Why is it important that those are held in place by an electromagnet? Not so much. What's going to happen to an electromagnet if the power fails? Yeah, it's just going to stop, right? It's going to stop being a magnet. So if the power fails here, these control rods are going to drop down and slow down the reaction. Okay? So you remember 2 years ago when there were those tsunamis in Japan and all those problems with their nuclear reactors? Okay? That's exactly what happened there. Okay? Tsunami caused power failures, tripped this, so the control rods fell into place and slowed down the reaction. What happened in Japan was a best case scenario for that type of accident. Okay? What was the worst nuclear accident to happen in the US? Does anyone know that? Oh, it's because it's too far away from here, isn't it? Well, there was one there, but the worst one was actually in 3 Mile Island in New York. Okay? Same thing happened. There was a power failure, all right? Control rods fell into place, all right? But there was still some nuclear fallout. Okay? No explosion, nothing like that, all right? Just a little bit of radiation leaked out. What was the worst nuclear reactor to happen in history? Chernobyl. Okay? Those crazy Russians, right? Okay? They didn't have this electromagnet system designed in their reactor. So they had a power failure, the control rods got stuck, all right? And now you have this reaction going out of control. Okay? Well, if you have this reaction going out of control, you have a bomb. Okay? And that's exactly what happened. This heated up too quickly, all right? Blew the lid off, spread radiation everywhere. Okay? But this is why I'm saying you shouldn't be too afraid of nuclear power right now, because nowadays we do have these control mechanisms in place, all right? So if there is a problem, these lower into place, slow down the reaction. But other than that, it's exactly the same as that steam locomotive. This reaction produces heat. The heat heats water, turns it to steam, turns a turbine to make electricity. And really the only thing you see of nuclear reactors are those big towers, right? I don't know. When I think of a nuclear reactor, I automatically think of the nuclear reactor on The Simpsons, right, with those huge, huge towers, all right? And even if you drive by any nuclear reactor, you're going to see these big towers. But all these are just recondensing that steam. So they're taking that steam, turning it back to water, and then starting this process all over again. But the only difference here is that the fuel we use is different. Now, can anyone guess, why do you think people like nuclear power? It's somewhat clean, all right? And I know that doesn't make sense, right? Because when we talk about nuclear reactions, okay, we're producing these byproducts that are radioactive. But can anyone guess that if I start with a pound of uranium, how much coal do you think I would need to get as much energy as I get from a pound of uranium? Talking about 10,000 tons, okay? So the energy density of this is so great, all right, that it provides much more energy than coal or oil or anything like that. But at the same time, we can have problems, which is why it's not super widespread. Now, a nice alternative to all this, well, if I can not misspell it, is fusion. Now, fission's when we take those big atoms and split them in two. That's what's happening in every nuclear reactor in the world. Fusion's when we take small atoms and combine them. So if I have two hydrogen 2,1 atoms and combine them, what's going to pop out of that?
4, which is B. No.
Remember, it's going to be 4,
Oh, no.
2, right? But that 2 is the important part. That's the atomic number. So helium. Okay. So instead of splitting a big atom, we're combining 2 little atoms. And just like fission, every time this happens, we release some energy. Okay? Well, I don't know about you, but I'd rather have helium lying around than radioactive krypton, iodine, xenon, and all that other stuff. Okay? But can anyone see the problem here? Why do you think this is difficult to do? Why is this difficult? If I had these 2 hydrogen atoms, each with 1 proton, 1 neutron, 1 electron, and tried to shove them together, what's going to oppose that? Yeah, the electromagnetic force. Those protons don't want to be next to each other. Those electrons don't want to be next to each other. All right? So I really have to shove them together. Now, once they do come together, they release energy, but it requires a lot of energy to get this started. So where do you think is the one place around that has a ton of energy to get this started? The sun. Okay? This is the reaction that fuels the sun. Every second, millions and millions of tons of hydrogen are being combined to form helium on the sun and releasing energy. And luckily for us, all right, the sun has enough hydrogen to keep this going on for millions and millions of years. Okay? But now, if our sun was a little bit bigger, we could actually have helium atoms combine to form something else. If 2 helium atoms combine together, what do you think they're going to form? Beryllium. Okay, 8,4 beryllium. And if we had a really, really massive star, okay, beryllium could combine with helium to form something else. What would it form? Yeah, form carbon. 12, 6, carbon. So really, no matter what we're talking about, whether it's natural radioactivity, okay, fission, or fusion, the same rules apply when we're looking at those reactions. Okay? We still have to have the same mass number on the left as we do on the right. Okay? No matter what it is. So today, not only did we get a first introduction in how nuclear reactors work, how everyone knows how a nuclear reactor works, we also got some basic astrophysics. All right? Because this is the same thing that's going on in every star. Okay? Different stars might be hydrogen, different ones might be helium, but these are the reaction that fuels every star in the universe. Okay? Any questions about any of this? No, we got this? Good. All right. So what I want you to do, all right, since that's all from this chapter, if I go back to this front eventually, all right, should be able to do all these different homework problems. Okay? And remember, these first 3 are just those tables we talked about that first week, being able to read the periodic table and say things like number of protons, neutrons, and electrons. And really, all these other ones are just balancing those equations that we've seen, making sure the mass number and atomic numbers line up. Okay? Good. So what we're going to start today, and when we have a decent amount of time for, is we're really going to start to transition into chemistry. Okay? This was kind of our bridge between the two. All right? These were just atoms and how these atoms interact. But the truth of the matter is that these atomic reactions are difficult. All right? To do these atomic reactions, we need a reactor, we need a star or something like that. But chemistry has been done for thousands and thousands of years. All right? Getting different atoms to come together isn't that difficult. So let's go ahead and start with that. So this is chapter 11 in your book. Okay? And since it is really our first chapter in chemistry, we have to go over a few basic definitions. Now, I know if you've had chemistry before, maybe even in high school, hopefully these will seem pretty familiar. And really, we've already seen some of these a little bit. Okay? The first thing we need to start with in chemistry is talking about the elements. Okay? And really, we already know elements, all right? Because elements are really just groups of atoms. Okay? So far, we've been thinking about the periodic table as representing individual atoms. And that's all right. We can think about it like that. I can think about an individual carbon atom as having maybe 6 protons, 6 neutrons, 6 electrons. All right? But I can also think about carbon as a whole. All right? So like the pencil lead in your pencils. Okay? That's not actually not lead, that's just carbon. So if I think about carbon on a bigger scale, I can call that an element. All right? So the element carbon would be composed of individual carbon atoms. Okay? The element iron, all right, would be composed of individual iron atoms. And so on. Same with everything on the periodic table. Okay? So an element, we just say, is a group of one type of atom. Not so bad, right? Now, really where we're going to spend most of our time in chemistry is talking about compounds. A compound, like an element, is just a group of molecules. But the problem here is we have to know what a molecule is. Okay? But that's not too bad either. A molecule is just 2 or more atoms chemically bound to each other. But just like with other things we've seen so far, all right, the definitions don't mean so much. All right, your book definitely has a bigger definition here. But what we mean by a molecule is that instead of just having a couple atoms in the vicinity of each other, there's actually a chemical bond between the two. And it's this chemical bond which is really going to be the focus of our next 3 chapters and our next 4 weeks in this class. Okay? And really one of the most common compounds around is water. What's the chemical formula for water? Yeah. H2O. Okay. So water is composed of 1 oxygen atom chemically bound to 2 hydrogen atoms. And there are a bunch of ways I can represent this. Okay. Well, maybe the most straightforward to start with is just say if we have 1 oxygen and we use a line to represent the chemical bond to 1 hydrogen to another hydrogen. Okay. So this is, if I think about 1 hydrogen molecule, it's 1 oxygen bound to 2 hydrogen atoms. But if I think of a glass of water up here composed of millions and millions of individual water molecules, then I think about it as a compound. All right? Not too difficult. Now, this is all well and good, but the truth is that there are an infinite number of molecules. And once again, we don't have to memorize every single molecule in this class. All right? Because anything that has this bond between 2 or more atoms is a molecule. So we have water, which we just talked about. But there's also ammonia. Where do you see ammonia? Yeah, like cleaning products. Okay. And that's just 1 nitrogen bound to 3 hydrogens. Okay. We have methane, all right, which is just a gas, a carbon bond to 3 or 4 hydrogen atoms. All right. So as long as we have these chemical bonds, it's a molecule. But like I said, okay, these are simple molecules. We could have 2 carbon atoms bound to 6 hydrogen atoms. We have 3 carbon atoms bound to 12 hydrogen atoms. Instead of one of those hydrogens could be a fluorine. So we can have these infinite combinations of different ones. But for the most part, we'll stick with some simple guys here. Now, way back in that first week, we talked about matter, right? This is taken right from your book. And we said matter was anything that has mass and takes up space. But that doesn't really do us very much good right now, because everything in this room is matter. So we need to be able to break it down a little bit more than that. And the first way we can do that is to say, well, matter can be split up into pure substances and mixtures. Pure substances, all right, fixed composition and properties, really that means it's just made of one thing. Okay? So like we just said, elements are made up of one type of atom, while compounds are made up of one type of molecule. So really, anything on the periodic table is an element. Okay? So like we just said, iron is an element. A compound made up of an individual molecule, so we just said water is a molecule. So water is also a compound. Now the mixtures get a little bit more confusing. Mixtures, we say, well, just mixtures. When we take two things and just mix them together. But we can have heterogeneous mixtures, which are not uniform, and homogeneous mixtures, which are uniform. Okay? Now, my favorite example of a heterogeneous mixture is really just a chocolate chip cookie. Because it's pretty easy to see in a chocolate chip cookie that there are cookie parts and chocolate parts, right? So since we have that non-uniform nature, then it's heterogeneous. Homogeneous mixtures are ones where you can't see a difference. There we go, salt water. Because I can tell real easily that if I have salt and water, those are two different things, okay? But if I mix them together, I'm still left with a clear liquid, right?
It depends on how much salt you use.
Okay, we'll say just a little bit of salt.
Because it just sinks.
Yeah, but if we say we don't add that much salt, all right, the only way we're going to be able to tell that that's not water is by drinking it, right? And then right away you can probably tell. Okay? So really, the best way to know these things is to just do a bunch of examples. So you have a couple of homework that have a bunch of examples, but we can also just go over a few examples here. Okay? Let's start with something easy. Italian salad dressing. Let's start on this side. Is there an Italian salad dressing atom on the periodic table? No, that's stupid, right? All right, there's definitely not. Is there an Italian salad dressing molecule? No, right? So we know right away this has to be a mixture. Okay, but if we look at Italian salad dressing, okay, is it uniform? No, not at all, right? If we let it sit long enough, there's an oil layer, there's a water layer, there's all sorts of seasonings and chunks of crap. Okay, so we can definitely say this salad dressing is a pretty easy example of a heterogeneous mixture. Okay? What if I had a chunk of gold? Big brick of gold up here.
Wouldn't be there long.
It wouldn't be there long, that's true. Okay? Which one's that?
The homogeneous mixture? No.
Is it on the periodic table? Yeah. So if it's on the periodic table, that means it's an element. Okay? Now, you're kind of right, because, oh no, I'm not wearing my wedding ring apparently, okay? But most jewelry isn't pure gold, right? What is it? We have a name for it. An alloy, okay? It's a mixture of like 14 karat, well, I don't even know, 14 karat gold, some mixture of gold and something else. Nickel? Sure. Sounds reasonable. Same thing with brass, all right? Brass is a mixture of copper and zinc, I think, all right? So all these different alloys are mixtures of metals. But at the same time, if I look at a 14 karat gold ring, I can't see those different atoms, right? I can't see that it's made up of these atoms and these atoms. So it's really a homogeneous mixture. So all alloys are homogeneous mixtures. And it's also a good point too. When we think about mixtures, we normally think about just liquids, right? But really, mixtures can be gases, liquids, or solids. It doesn't matter. Okay, let's try a trickier one. We've had some Dr. Pepper here. Open a can of Dr. Pepper and pour it in a glass. Is that an element, compound, homogeneous mixture, or heterogeneous mixture? Well, can we eliminate one right away? There's no Dr. Pepper on the periodic table, right? It should be. Okay.
Could it be one of both sides?
It can't be two things, remember? At any one time, it has to be one. What do you think it is? I promise we won't laugh at you for being wrong.
The homogeneous, because you can't see the mixture, and it's a liquid.
Well,
A compound
It also
too,
is a
'cause it's
compound.
different elements.
It is.
okay. But if I pour that Dr. Pepper in a glass here, is it a uniform mixture? What is that going to have in it? It's going to have all sorts of bubbles, right? It's going to have that carbonation, right? Even if I just sit it there, I mean, you're eventually going to see bubbles come up, right? And so because it has those different bubbles, it's definitely a heterogeneous mixture. Okay? But if I left it there long enough, what's going to happen to that Dr. Pepper? It's going to go flat. Okay? And now really, what is Dr. Pepper? It's sugar water, right? Let's not kid ourselves. Any soft drink is just sugar water. Okay? And so sugar is a compound. Sugar is a molecule. Okay? Water is a molecule. But when you mix them together, it's a homogeneous mixture. Okay? So really, I can put sugar water down here as being a homogeneous mixture. Now you're right. Okay? When we have mixtures, they can be combinations of different things. But it's because they're those combinations that they are mixtures to begin with. Why don't you guys give me a couple? Anything, something in this room, maybe something that's tricky. Yeah.
What's bleach?
Bleach. Okay. Bleach is probably a homogeneous mixture. Okay, because bleach is actually yeah, you got me. All right, it's some compound mixed with water. Okay, so bleach would definitely be a mixture. Ooh, now I'm gonna have to actually look that up.
Like acetone.
Okay, acetone. All right, that's something you might have used in a lab. Okay, acetone is really a molecule, so acetone would be a compound.
Soil.
What?
Soil.
Okay, soil. What do you guys think?
Heterogeneous, separated.
Yeah, that's probably true of anything. If we go up there and pick up a handful of dirt, okay, we can definitely see that there's different parts to it. Even if it's all the same color, we can see that there's maybe little chunks, okay? So soil would definitely be a heterogeneous mixture. Okay, I got a kind of tricky one for you. What about the air in this room?
Homogeneous mixture.
Told you it was tricky. Okay. No. Well, okay, let's think about the air in this room. Okay, you're on the right track because it's definitely a mixture of oxygen, nitrogen, carbon dioxide, maybe a little argon. Okay, let's say I turn off all these lights in here and turn on a flashlight. What are we going to see? We're going to see a bunch of dust in here, right? Okay, so really the air in this room is a heterogeneous mixture. Okay, because if we look close enough, we can definitely see dust, definitely bacteria and all sorts of other crap floating around in here, dead skin cells, all right? The air in this room is actually pretty disgusting, all right? So it's definitely going to be a heterogeneous mixture.
What if there's none of like like it's in a vacuum?
Well, if you have like a clean room, yeah, that's what you're thinking of, where those people wear the big white suits and everything, cover their mouth, yeah. But even then, okay, like a really good clean room is like a class 10 clean room.
Why they get classes?
Yeah, they have different classes of it. Yeah, because like if you think about it, like I don't know if they have a clean room over at McNeese or not, If they had one there, it may be a class 1,000. And that would mean you don't have particles smaller than 1,000 micrometers. Okay, or maybe there's only 1 in 1,000 or that size. Class 10 means you don't have any particle bigger than 10 micrometers. Okay, and that's something you find at something like Intel or something, like high, purity standards. But here, what do we have filtering the air in here? Maybe crappy filters that haven't been changed in 2 years. So here, we're not very clean. Because even if you think about outside too, especially this time of year, if you look close enough, you're going to see pollen and all sorts of other crap in the air. And hopefully if we start to think about this, really most of the stuff around us is going to be this heterogeneous mixture of different particles. Okay? Really everything is. Even in this room, if I look at this tabletop, okay, I can see the different grains in here. That's heterogeneous mixture. Okay? My shirt, okay, will even just be as a dye, and there's different colors, that's going to be a heterogeneous mixture. Same with anything. Okay? So what I hope we can do from this, and what there's a couple homework problems on, is just identifying different things and saying what type of mixture it is, or whether it's an element, compound, heterogeneous mixture, homogeneous mixture.
So how do you know whether it's going to be a compound or a mixture?
Okay, well, a compound is just made of one type of molecule. Okay, and so as we go forward, we're going to learn more and more molecules. Okay, but right now we don't know a ton. Okay, because I can say the compounds we've talked about water. There's carbon dioxide, okay, which is what we exhale. We talked about acetone. Ammonia is NH3. Rust is Fe2O3. There's all sorts of different compounds, and as we go forward, some we're going to use more than others, all right, and we'll eventually know them, all right, and that is kind of tough. These elements are easy. Just look at the periodic table.
A compound's always just two elements together.
It's not always. It's two or more. Okay. So whenever you see it written like this, all right, the chemical formula, which we'll go into probably Wednesday, all right, then you know it's going to be a compound. Because what I mean when I write it like this is that there's actually a chemical bond between those two. So like in this room right now, there's nitrogen, oxygen, and all sorts of other things, but there's no nitrogen chemically bound oxygen. If I were to actually do a chemical reaction and bind those together, then it would be a compound. But what's going to help us with this, hopefully, all right, is if we spend a little bit more time reading off the periodic table. Okay, because so far we only know a couple things, and we're not going to have time today to finish this up, but we can start today. All right, and that's why this periodic table here isn't the best in the world. So I really do recommend that you bring your books, if hopefully you have them. Okay, because the periodic table in your book isn't bad. Okay, because if we look here, there's actually a lot that we haven't talked at all about yet. We know that this top number is the atomic number and tells us the number of protons. And we know that this bottom number is the atomic mass. That tells us the average mass of every, what I point to, every vanadium atom in the world. Okay?
Why don't we write it like that?
What?
Why don't we write it like that?
Because the periodic table is presented in, it's not standard. Okay? The shape of it is, but, yeah. But when we say something like carbon 13-6, if you write that anywhere in the world, people are going to know what that is. Okay? Because the mass number is always going to be on the top, atomic number is always going to be on the bottom. Okay? And it doesn't matter. Even if you're in Japan, China, wherever, all right, they're going to write it like this. Okay? But the periodic table is going to be slightly different. Some people put the atomic number here, some people put it to the left, right, whatever. Okay? But the shape is always going to be the same. And so one of the first things we can get from the periodic table, well, I don't need to just write that, all right, is we can start to think a little bit more about the electrons. Because I know right away, if I look at the periodic table, I have the atomic number, which tells us in a neutral atom, all right, how many electrons I have, right? So I can tell pretty easily that carbon has 6 electrons because it has 6 protons. Fluorine has 9 protons, 9 electrons. Okay, that's all well and good. okay? But really, we don't care about all of those electrons. We only care about a few of them, the valence ones, all right? And now I'm going to give you another ridiculous example to think about so we remember valence electrons. Valence electrons are those electrons on the outside. Let's start there, on the outside. All right, let's pretend that we have some mother by herself with 8 children of similar ages, okay? Okay, she's a little overwhelmed, right? Let's say they go sit down at church in a big pew, okay? Such that the mother's here, all right, 8 kids are all lined up beside her. Which of those kids is going to be the most, right way to put this, which one of those kids is going to misbehave the most? The one on the end, right? Because if you have a kid right next to her, I mean, she's going to keep that kid in line. It's going to be harder, though, the further and further and further we go. So those kids on the outside are going to cause the biggest problems. Well, it's the same way when we think about atoms, okay? When we think about atoms, those electrons the furthest away from the nucleus are going to be the ones that are most likely to undergo different reactions. Because when we talk about chemical reactions, it's really the electrons that are undergoing these reactions. And this is where the periodic table is going to help us, okay? Because unlike how we saw before with just one orbit, all right, we actually have a bunch of different orbits for these different electrons. If I start at hydrogen, okay, hydrogen has 1 electron, okay, and that 1 electron is going to orbit around hydrogen. If I move over to helium, helium has 2 electrons, okay, and they both share a similar orbit, okay, but this first orbit for those electrons can only fit 2, all right? So when I go on to lithium here, that first orbit can only fit 2 electrons. I don't have room for that 3rd electron. So I have to create another orbit. So now I have 1 orbit with 2, all right, and 1 with 1. So with beryllium, with 4, I can fit 2 in the center, and then 2 on the outside. And we keep going, we keep going, we keep going until we get to neon. Well, guess what? Neon, that 2nd orbit can only fit 8. So when I get to neon here, I have 2 electrons in this first orbit. 1, 2, 3, 4, 5, 6, 7, 8 in that second. That is beyond the scope of this class. It's much more complex than this, such that, well, if we think about it to begin with, all right, which orbit's going to be bigger, all right? Yeah, the further you go out, you're going to have more room, all right? And that's not totally true when we think about atoms, but it's mostly true, okay? Such that the shape of this first orbit is really more of a sphere, okay? And it can only fit 2 electrons. The whole periodic table, every single atom, all right, that first orbit around the nucleus can only fit 2. Okay? This next one can only fit 8. Okay? And really that holds true for all of these what we're going to call main group elements. So we're going to talk about the elements here and the elements here. We're not going to worry about all this other crap. Okay? So what this means is that once we fill up one orbit, we have to start another one. Okay? Well, for these main group ones, this last orbit can only fit 8. All right? So all these orbits are going to fit 8 in the second. So yeah, we go 1, 2, all right? We have to start again and start again. But it's these electrons on the outside, which we're going to call valence, which are going to be the most important ones. So while, where's that? Lithium has 3 electrons total, I really only care about this 1 electron on the outside when I'm talking about chemical reactions. Okay? Same way with beryllium. Beryllium has 4 total, but I really care only about these 2 on the outside. Because these 2 in the middle, all right, are close enough to the nucleus that they're not going to react much. So really, if I look at the periodic table, just by saying where it is, I can say how many valence electrons it has. Because the first thing we can say when we look at the periodic table is that it is split into rows, right, and columns. Now, of course, this is science, so we have to have more ridiculous names than just rows and columns. Okay? So we're going to call the rows periods and the columns groups. So we have periods and groups. But these are actually going to help us, okay? Because if I look at hydrogen, okay, how many valence electrons does hydrogen have? 1, right? Because it only has 1 electron, so that electron is the one on the outside, okay? How many valence electrons does helium have? 2. Well, then I start back over again, and I have lithium. Well, here, it's probably easier to see over here, okay? Lithium has 3 total electrons, but only 1 of them is on the outside, okay? Beryllium has 2, 3, 4, 5, 6, 7, 8. That one's full. I have to start back over at 1, 2, and so on. So really, it's this group number here that tells us how many valence electrons we have. Okay? And so it's a little bit different in your book, but if I look at the A's, so everything in group 1A has 1 valence electron. Everything in group 2A has 2 valence electrons. Everything in group 3A, 3, so on and so on. Okay? So we don't have to go through this nonsense of drawing out these atoms every time we want to talk about a chemical reaction. All I have to do is look at the periodic table and say, okay, iodine. Iodine is in group 7A, so it has 7 valence electrons. Okay. Boron's in group 3A, so it has 3 valence electrons. That's it. Not too bad. And so that's what the groups tell us, but the periods actually tell us something too. Okay? Because if I look at hydrogen, how many orbits does it have? How many orbits for those electrons does it have? 1, right? Because it has 1 electron in 1 orbit around the atom. Okay? Helium has 2 electrons, but they're only in 1 orbit. Well, now if I go to lithium, I had to add another orbit, right? So now I have 2. Well, I have 2 orbits all along here until I'm full, and then I go and I have 3, then 4, and 5, 6, and so on. So this period number here tells us how many orbits I have for these electrons. The group number tells us the number of valence, and the period tells us how many orbits. So let's try this. So once again, the only way to get good at this is practice. Let's pick something at random. Okay? What about fluorine? Okay? So we're going to do this with a bunch of things. And I want to know how many electrons there are total. So total electrons, how many valence electrons, and how many orbits for those electrons. How many total electrons does fluorine have? 9, right? Has an atomic number of 9, so it has 9 total electrons. How many of those electrons are on the outside? How many of those are valence? 7. It's in group 7A, so it has 7 valence electrons. Okay. How many orbits does it have? 2. Good. Okay. Let's try barium. How many total electrons does barium have?
It has to be 6.
56. How many of those are valence? 2. How many orbits does it have? 6. Good.
How old is the periodic table?
It was, this is in your book. It was first developed in the, let's say 1700s or 1600s? Well, yeah, because that's the thing about this, though, is that when the periodic table was first developed by Mendeleev, all right, he didn't have, there were tons of gaps, all right? Exactly, all right? Because, all right, because the valence electrons dictates what the chemical properties are, so if you have carbon and silicon, all right, should behave similar, whatever that is, should behave the same, okay? So it all, and so he found out that there were gaps, and then later they discovered those atoms, and they said, hey, that has similar properties. And this really was a breakthrough for its time, because it doesn't make sense on a common sense level. Because if you look, things like carbon and nitrogen should behave the same, okay? Because really there's only one proton difference between these two. But carbon at room temperature is a solid, nitrogen at room temperature is a gas, okay? But if we start looking at these other things, like there's not a lot of sameness across the period, all right? There is, though, when we look up and down. Like if we look over here in group 8, okay, we'll talk more about why these are special later, but helium, neon, argon, krypton, xenon, these are all gases, okay? They're all gases, they all behave very much the same, all right? The same way with hydrogen, lithium, sodium, and potassium. These are all very reactive elements, right? They all behave somewhat the same. Okay. And this is why I said we don't need to ever memorize the periodic table, but we need to learn how to get this information out of it. Okay? Because if I tell you, what if we do the inverse of this? Okay? If I tell you what atom has 3 valence electrons and 2 orbits for those electrons? Now, which one has 3 valence electrons? So which group is that going to be? Well, no. It'll just be 3A. So everything in group 3A is going to have 3 valence electrons. Okay. And so 2 orbitals, everything in the second period is going to have 2 orbits. So the only thing that has 3 valence electrons and 2 orbits is boron.
Is that how you know between A and B, just pretty much whatever has that many orbits?
Don't worry about the B's. Okay? No. Okay? Because like I said, these rules hold for these main group or representative elements. Okay? So they hold for group 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Okay? These guys behave a little differently. Okay? Let's try a couple more. Okay? What about 5 valence electrons with 5 orbits? Yeah, SB, 10. I know that doesn't make much sense, that's 10. But No, that's not 10. Sn is 10. I have no idea what Sp is. Okay. What about 1 valence and 3 orbits? Yeah, sodium. Okay. And this is what I want us to be able to do when we're done here, is be able to pull out this information. So let's try to expand this a little bit more before we're done today. How many of us are here? 8. We might be able to do this. Okay. Let's go around the room and start talking about sulfur. Okay. We might be able to get to 8 things we know about sulfur so far. Now, let's start over here. Tell me one thing about sulfur. Let's see. Well, from the periodic table, what's something we know about sulfur? Well, it's your hometown.
It has 16 protons.
Okay, it has 16 protons. Okay.
16 electrons.
16 electrons total. Good. All right. Kivian.
Where's it at?
That's right. It's right here.
Oh, all right. It has a mass number of 32.
Not a mass number.
Atomic.
It has an atomic mass of 32.064. Okay. What else we got? Well, we can't say that so much. We can say maybe on average it has 16 neutrons. But remember that atomic mass tells us the average for everything. So some sulfur atoms might have 16 neutrons, but some might have 17. Okay? What else can we say?
Starts with S.
It starts with S.
It has
Well-
3 orbits.
Okay. It's in period 3, so it has 3 orbits.
And 6.
Yeah, it's fine. And it has 6 valence electrons. Okay? Good. That is what I want us to be able to do. Okay? And so expect something like this on the quiz on Wednesday. Okay? And as we go forward with this chapter, we'll know even more. All right? But I want us to real quickly just be able to look at these and be able to say a bunch of things about them. All right? And we could even say, well, if it's Cl, all right, its name is actually chlorine, atomic number, mass number, and then the atomic number means this, and the atomic mass means this. Sorry. Okay. So what you should be able to do then is those nuclear physics questions from before, as well as these first couple homework assignments. And now 1 and 2 are just identifying whether something's an element, compound, heterogeneous mixture, or homogeneous mixture. And then 11 and 12 are just more that, all right, how many orbits does this atom have? How many valence electrons, and so on. Okay? Any questions about anything we did today? Okay, I'll see you guys on Wednesday.